Hi, I'm Tristan from the Samsung AI Center in Toronto, and I'm going to talk about our work on cycle-consistent generative rendering for 2D-3D modality translation. The inspiration for our work comes from the famous Cycle-GAN model, which learns a two-way mapping between image domains, such as between horses and zebras. Through a cycle consistency constraint, Cycle-GAN learns a domain translation model from unpaired images alone, greatly simplifying data requirements. Given the success of Cycle-GAN, a natural question is whether we can apply this to translating between the modalities of an object in the same way, in particular, mapping between 2D and 3D. So without paired data, we need to learn a shape-to-image translator, which effectively solves a graphics problem, and an image-to-shape translator, which performs 3D computer vision. Learning these two functions is the goal of our work. Now, part of our motivation stems from the difficulty in obtaining 2D-3D paired data. For instance, finding an exact 3D shape and aligning it into an image can be quite hard. However, we do have much more abundant sources of unpaired 3D shape and 2D image data, which is fortunately all we need to train our model. So taking this approach confers several benefits. First, we do not require paired data. Second, we can actually generate paired data from unpaired. And third, our algorithm learns single image 3D reconstruction as a byproduct of its formulation. In terms of training, it works just like Cycle-GAN. Using point cloud and masked image data, we learn mappings between 2D images and 3D shapes. In our model, 3D shape is a graphics code consisting of rigid pose, a deformed 3D mesh, and a texture image. However, we do not require camera information or 3D textures at training time. For results, the image-to-shape mapping performs single image 3D reconstruction. Here we show input images in the red boxes, as well as the model's output from several views. On the other hand, our shape-to-image translation learns to do generative modeling of images. In the green boxes, we see real 2D images, while the remaining insets are random samples from the model. Finally, our model automatically disentangles shape, pose, and texture all in 3D. Starting from encoding the boxed real images in the corners, we smoothly interpolate latent texture along the horizontal axis, whereas we do so for latent shape and pose along the vertical one. And that's all. Thank you for your time.